Mhm. Okay. Yesterday we discussed that when we consider equation with interaction, we face several problems on the way of looking for stationary solution. And today we will consider what can be achieved if we apply usual machinery to equation with interaction. And also we will see a new notion of shift compactness, which can substitute stationarity for for solution to equation with interaction. So this is the general form of equation with interaction. Here we have a presence of mass distribution of all particles in the system, mu t, in the coefficients. And yesterday we discussed that firstly, the space of probability measures is not locally compact. So if we just guarantee that mu t are bounded in Wasserstein distance, which can be achieved via boundedness of moments of the mappings xu t, then we cannot guarantee that we will have some invariant distribution because we have no compactness. Also, we discussed that the coefficients, especially coefficient A, usually are multiple integrals which respect to measure mu from differences between values of x in different points. So it is not natural to expect that such coefficients will contain term which push all particles to zero, for example. But let us start from consideration of such case. So to get a stationary solution, let us suppose that our coefficients which are responsible for external force and for interaction between particles, A u mu has the following. It is minus alpha x ut plus A with tilde x ut mu t. So we just add special term minus alpha x ut, which push all particles to zero. And I consider alpha positive and sufficiently large. What means sufficiently? As yesterday, alpha must dominate, which is constant for A tilde and B in order to have strong force which push all particles to zero. Yesterday we have seen that in case of ordinary stochastic differential equation, such term minus alpha x ut gives us existence of the stationary solution, especially in famous linear case when we get in such a way a well-known Stein-Uhlenbeck process. So here, if we consider the approach which we used before, so we have to consider Cauchy problem, which start at the moment f. And one can check that again, as before, there exists a limit under s tend to minus infinity x ut, in square mean, in a mean of any order, and so on. And this guarantees existence of the stationary solution and even uniqueness of this stationary solution. But due to such strong push into zero, it occurs that for any U1 and U2 starting points from RD, if we consider the difference between the solutions which start from U1 and U2 at time S, and we will consider this difference at time t, then the limit when S tends to infinity is equal to zero. A stationary solution has the following form. Mu t is concentrated in one point. All particles of our system in stationary case are glued up together, and we have some stationary process psi t, and this large particle and fat particle just move around the space. That's all. So we have seen that such addition of external force, which push all particles to zero, is not very productive. Yes, the stationary solution exists, but all particles glue up together in one heavy particle. So it is not an idea at all to consider such coefficient in order to have stationary solution. Of course, we can slightly modify this idea in such a way. Suppose that we will have as attracting center different points for different starting points. Because here, in this coefficient, the attracting center is an origin. But one can consider a more general case, and let me propose it to you. Here is this such form of equation with interaction. You see, mostly the same equation, but here with this alpha we have term x ut minus u. It means now that this term push every particle to its initial position. In this case, we also exactly as the same with the same approach as before, can prove existence and uniqueness of the stationary solution. And in this case, there are no such effect as a gluing of all particles together. But somebody can say that the idea of such attracting centers for different particles seems to be artificial, because before, when we introduced the equation with interaction, we said that these coefficients A and B are responsible for interaction with between particles and interaction with random media. And we already discussed even today that the usual form of the coefficient A must be some multiple integral containing the differences between xu for different points u. So it looks for the first time that this additional attracting center are artificial, but it occurs that people doing this and a relatively long time ago, for example, Funaki in 80s of the previous century proposed such a model of the interacting oscillators in random media. You see the equation, And this equation is for motion of such particles which are placed on the vertical lines, which we can see in the picture, and connection between particles is like satisfy Google law. So we can see this term which is responsible for interaction, and we can see the noise beta I. Then, when we add the same term which push every particle to its position at the origin, then we will get stationary solution for this equation. Even more, Funaki did some limit produced some limits for this model when partition of the interval increases, the noises are correlated in some way, and so on. But now the most important thing that every particle is oscillating near its origin, so near its own attracting center. So as I said, the idea of attracting center is not too artificial as it seems from the first look. But still, it is desirable to have something for such coefficients which are responsible only for multiple interaction between particles and does not contain any special force which push particles to some point. Yeah. So we have not even external influence to guarantee stationary behavior. Last lecture yesterday, we have seen that in this case, we cannot expect stationary behavior in general. But what we can expect that the measure ut will not spread along the space, but will float along the space near its center of mass or some other point. So let us make some definitions which are corresponding exactly to this behavior. And now we will consider shift-compactness of probability measures. Definition. The set of measures mu alpha in the Wasserstein space of fixed order m small is shift-compact if for every alpha there exists the vector u alpha belong to Rd such that the family mu alpha minus u alpha is precompact. So this is exactly case which we discussed before at the end of the lecture. We consider the family of measures. These measures can be shifted along the space in a way, but we can move every measure in such way that new family will be compact. So this is a simple definition, but we have to study it a little bit from different point of view. For example, how to find this U alpha. And of course,
I'm sorry. Can you please clarify how you make a subtraction measure minus vector? You mean delta measure?
Yes, this is a good question. Here, mu alpha minus u alpha is a shift of mu alpha on the vector u, and this is a new measure which is defined as follows: mu alpha minus u alpha from some set delta is exactly mu alpha from delta plus u alpha.
Thank you.
So, as I said, the vectors u alpha can be chosen in different ways. Maybe we have to invent some canonical points for mu. And it is true. For example, for the space M0, consider the following definition. The vector u belonging to Rd is called by the center of the measure mu if if delta measure concentrated at this point, delta u, realize the minima of distances between our measure mu and different delta measures on the space. It can be proved that this minima exist. And of course, there are sometimes there are not only unique, there are, but at least have characterization of such points. It is center of the measure. Please note that we don't require any moments from the measurement. The center can be defined for arbitrary measurement. So, take at least one C alpha for mu alpha lemma, and if the family mu alpha is shift compact, then mu alpha minus its center C alpha is precompact. So we always can check as a candidate for u alpha when we study shift compactness. Then we can use these centers of measures. Now consider deterministic equation with interaction where such shift-compact family of measures arise naturally. Consider such differential equation with interaction. Here you see dxut equal pi dt minus integral of r, this one-dimensional case, arctangents of xut minus v, mu t dv dt. As usual, mu t is an image of mu zero under the mapping x. It is trivial to understand that xut tends to plus infinity for every u when t tends to plus infinity. From other case, if we consider the differential of the square of difference xut xu1t minus xu2t, it is negative. It means that there exists a limit fu for any point. This is a distance up to the point which started from 0. Then, if we consider shift of mu t and x0t, it will be an image mu 0 and f minus 1. It will tend to mu 0 and f minus 1. So we see that the family mu t now is shift compact. I propose the one candidate of the shifting family x u0t. Yeah? This gives us understanding that maybe in stochastic case we will have the same. And now let me propose to you definition of the shift compactness in the stochastic case. Actually, it is more or less the same. The set of random measures mu alpha from Wasserstein space of any order is shift compact if for every alpha there exists a random vector now zeta alpha such that the family of random measures, oh, this is my fault, here must be mu alpha minus zeta alpha, this random vector zeta alpha, not u, is weakly compact in M. Of course, this definition can be easily produced from the previous one, but it is desirable to have some at least sufficient conditions for shift compactness of the family of random measures. We will not look for a general case of arbitrary family of random measures, but we consider the case which is closely connected with equation with interaction. And one of the possible way to make such connection is to consider a special family like this. Suppose that we have a family of random measures which are organized in such way. We have one starting measure mu0, and we have a family of random mappings f alpha, and mu alpha is just image of the measure mu0 under the random mapping f alpha. You see that the situation is exactly as when we consider the equation with interaction, because in case of equation with interaction, we have mu t, which is an image of the initial measure mu0 under the mapping xt. So if we have such condition that expectation of f alpha u minus f alpha v in m plus 1 power is less than norm of u minus v in m plus 1 power, then for mu0 belonging to m plus 1, the family mu alpha is weakly compact in mm. Here is only one remark related to this plus 1 in the indices of the space for mu0 and in the powers in the condition for function f. Why we have to add something to m to have weak compactness in the Wasserstein space and capital indices by m? The reason is following. You remember that we described weak compactness in Wasserstein space, and during this description, we use the family of functions jk, which have a growth at infinity like norm of u in power m. And we need we need to estimate the integral from this function with respect to our measures. And we do this using Hölder condition. So we need something slightly bigger than m in powers. But we consider with u only Wasserstein space with natural or integer index, so we use plus 1. This is an explanation. But nevertheless, we have such a condition. And by the way, let me note, then under a very natural condition on the coefficients of the equation with interaction, you remember we just say that xut, solution to equation with interaction, is diffeomorphism, but it under the Lipschitz condition for the coefficients, it can be proved that we have such estimation like is written for expectation for difference xut minus xvt norm in m plus 1 power, because this is the relation responsible for the smoothness with respect to spatial coordinate. This is the explanation why we have not different power in the right part. Because if we consider the smoothness with respect to t, of course, we will have very different inequalities. Okay. Then consider the equation with interaction, and you can see the equation with double interaction. Yes, Here we have a function phi small, which is responsible for the double interaction. And as you see, we have no any additional terms which will push our particles to some point or to some different points. We just have the general form of equation of interaction. Only this one Wiener process dw, but this is written for simplicity. It does not matter. It can be written in general form with the Gaussian measure instead of one Wiener process. And now the following theorem becomes to be true. Suppose that initial measure mu0 is in the space m capital m small plus 2. And this phi satisfies such coercitivity condition that the inner product of the difference of arguments on difference of phi's let B be a Lipschitz function with respect to both variables x and mu, and the constant with the constant B capital. And we have such a technical condition that, as I said, alpha must be sufficiently large in case of Rothstein-Uhlenbeck and its nonlinear analog. Here we also must have alpha from this condition to be sufficiently large in order to have such inequality. Then mu t, which are obtained from this equation, is shift compact family in MF. So you can see that guarantee the shift compactness via the conditions of the coefficients, and now the coefficients seems to be more natural for equation with interaction because we just have double interaction between particles. Of course, it must be noted that this theorem can be generalized as follows. We can add some general coefficient plus a, which depend on x and mu t in a more complicated way. And of course, we will need that alpha is such that it will dominate not only Lipschitz constant for coefficient b, but also Lipschitz constant for coefficient a. So it must be noted that this is just example to show how it works, but we can add general coefficient and consider general form of equation with interaction and guarantee that obtained family of measures mu t will be shift compact. Now how we can use it? Of course, we have no stationarity, but one can consider special type of functionals from measures. For example, one can consider such a phi, which acts from Wasserstein space to R, which is continuous and has the following property. Phi from the measure mu shifted on the sum vector is equal to initial phi. Then, if the family mu alpha is shift compact in the space M small, then the family of random variables is weakly compact. So one can control the distributions of the functionals from such kind of functionals from our measures mu alpha. And let me note that these functions, such functionals are very natural. As an example, one can consider the following functional, and this functional is related to for example, a self-intersection, generalize the self-intersection of our measure mu. And in particular, it can be internal energy of the system. Here is example of such function, and it is natural to look at it. And now we know that under the condition of the proposed theorem, internal energy of the mu t organize a family of weakly compact variables. So one can say that it can grow up. It can grow up, for example, infinity or so on. One can guarantee this. Okay, now we have seen the substitution of stationarity, like shift-compactness for solution to equation with interaction, and it is the time to go to applications. As applications, I will propose to you today and tomorrow several models based on the equation with interaction, where we will check the properties of the model using the tools which we discussed during our lectures. So let us begin with the application. And the first one will be devoted to the motion of the curve or surface in the random media, which can be described via equation with interaction. Consider a curve gamma 0 in R3, which is parameterized by S from 0, 1. So this is just a continuous mapping from 0, 1 to R3. I will suppose that it is closed, so gamma 0 from 0 is equal to gamma 0 from 1. At the moment, I don't need any smoothness, but further, I will suppose that the gamma 0 is a smooth periodic function. How to move the curve using equation with interaction, and why we have to choose equation with interaction to describe the motion of the curve in the random media. This is natural because when we move the curve in the random media and consider some separate point of the curve, it moves under influence of different forces. One is the influence of random media, or the force of the liquid. Suppose we have some flow of liquid and put our curve in this flow. But from other side, it interacts with the other points of the curve. So we have interaction, and we have influence of random media. How to use the equation with interaction to describe the motion? It is pretty simple. Let us define the visitation measure of gamma 0 as follows. For any set delta from R3, define mu 0 of delta as integral of the indicator of delta from gamma 0 as ds. Here, we have the indicator. And if we just interpret for the moment, interpret S as a time, inner time for our curve, then this integral is the amount of time which our curve spent in the set delta. This is the explanation why we use the term visitation measure. So what time gamma 0 spent by visiting our set delta. Now consider the equation with interaction with this mu 0 as initial measure. So this is a general form of equation with interaction, and we have mu t as an image of mu 0 and x. I must say that the interaction between parts of the curve were introduced and were introduced to equation for its motion, firstly by Landau and Lifshitz in their well-known filament equation, but they put attention, they considered only interaction with infinitesimal neighbors. So it contains first and second derivative of the equation of the curve with respect to parameter, and the motion of the curve has a very special feature. I will say about this later. And it turns out that in this case, if we define in this way mu t, then mu t became to be a visitation measure of gamma ts, new by our law. It's natural and it is easy to check. So in this way, we can describe the motion of the curve just putting as initial measure the visitation measure of this curve. Exactly the same can be done if we consider instead of the curve the surface which is parameterized by two parameters. We can move it in our space R3, or more generally, we consider some manifold in multidimensional space. Again, we can define its visitation measure and produce the same picture. So let me emphasize again that the presence of mu t in the coefficients reflects the interaction between the different parts of the curve during its motion. The essential feature of such model is the following. The curve cannot organize new self-intersection during its motion due to the diffeomorphic property of xt. You remember that when we only introduce the equation with interaction, we just discuss that x ut under the good smooth coefficient with respect to spatial argument keeps diffeomorphic property exactly like the flow of solutions to ordinary stochastic differential equation. Since x is diffeomorphism, then it can glue up points. So if our gamma 0 has no self-intersections, then gamma t for sure will have no any self-intersections. Consequently, gamma t does not change its topological type. For example, if it will be a knotted curve, then it remains to be a knotted curve. It can change its shape, but its shape from topological point of view remains to be simple if it is unknotted. Yeah? Okay. So we have, if we want to have a good model of moving curve, we have to overcome this difficulty. Why? Because in the nature, especially in polymer producing, we have possibility for random curve to change its type. For example, DNA, due to its double spiral structure, has property of self-crossing, and so DNA can change its topological type. To overcome such a problem, we can include additional randomness into model. Suppose that Xi from R3 to R3 is a centered Gaussian random field with independent coordinates. which have a covariance function like this. Phi uv is equal to exponent minus 1/2 u minus v squared. This means that Xi has two essential features. One is following. Xi is smooth mapping because of its small infinitely differentiable covariance. From other side, Xi has covariance which rapidly decreases when u minus v, when the norm u minus v tends to infinity. So the values of Xi on different domains of R3 are almost independent. Because you remember that for Gaussian processes, the covariance is responsible for independence. Yeah? Now consider a new curve. Gamma t is xi from gamma t small. So how this additional randomness, which comes from xi, can be interpreted? We just move our curve along the space. But then, because everything is very small, like molecule of DNA or other polymer, then when we just try to look at this fixed molecule, we have additional random perturbation. Yeah, and this is Xi. Yeah. So now it can be proved several facts. Firstly, that at fixed time t, gamma t has no self-intersection. So at fixed with probability 1, at fixed time, gamma capital T has no any points of self-intersection. But it can be also proved that gamma T changed its topological type at random moments. The situation is exactly like situation with one-dimensional Brownian motion. If you remember basic properties of one-dimensional Brownian motion, you remember that under fixed moment of the time, probability that it is equal to 0 is equal to 0. But it has a lot of roots in random moments of the time. Yeah? So exactly the same happens there. And moreover, due to the structure of covariance, which we already discussed, it occurs that gamma capital T, can have very different topological types and can have any topological type. So if we draw arbitrary node, the probability that at some time t, gamma t will have topological type like this node is positive. Next lecture we will study the properties of gamma t related to stationarity. Discussed today, we have something which substituted stationarity, but I want to end this lecture with a picture of modeling of evolution of gamma t. So let me do this. By the way, this picture was produced by my student Katerina Kustareva and produced using the mathematical arguments of approximation of Gaussian measure W, of approximation of the random field psi, and so on. So it is a product not only like movie for kids. It is a mathematical product based on the mathematical consideration of a discrete approximation of equation of this interaction and discrete approximation of the random field psi. Let's see how it evolves. So you see that it changed its topological type from a simple one, but to knotted, and again. So you can see that the proposed model really describe the motion of a random curve and the random media. Let me go back to lecture. Actually, this is all what I wanted to say today. When t tends to infinity, and discuss some other models based on equation with interaction in order to have a feeling of application of asymptotic analysis of equation with interaction. Today that's all. Thank you for your attention. And maybe somebody have questions and comments, please. Okay. If there are no any questions, then let us meet tomorrow and see the properties of this model and study some other applications of equations with interaction. Thank you.
Thank you.
Thank you for your attention, and bye.
See you tomorrow. Bye.
К сожалению, я завтра не смогу присутствовать, я буду в процессе
Да.
поездки. Так что,
Я запишу, да, так что.
да. А потом будет где-то available на YouTube у вас в канале или где?
Да, я уже выкладываю, уже все есть. Ну, и сегодня.
А слайды?
Слайды мне еще не прислали.
Ну, надо, как сказать, стучите, и вам отворим.
Хорошо.
Попинать лекторов, тогда они пришлют слайды.
Да.
Кстати, еще один вопрос. А вот на следующей неделе лекции планируется записывать?
Ну,
тоже как-то?
мне сказали, что да, что будут записывать. Так что...
То есть надо как-то девайсы, то есть, как сказать, мне заходить в Zoom как бы с компьютера, да, и как бы читать лекции вот в Zoom.
Да нет, вроде в реальности, но они как-то это запишут, как я поняла. Наверное.
Ну, просто чтобы мне тоже за девайсами разобраться. То есть вопрос в том, надо ли мне писать на доске или там какой вообще, что там есть. Там, если там доска, где там писать? Или мне надо вот на экране что-нибудь, если надо будет писать?
Ага, а у вас слайды или вы все планируете?
У меня слайды, но может быть что-то, если надо там как-то более детально прокомментировать. Я не думаю, что там будет сильно много, как сказать, записей. Ну вот в духе того, как Георгий делает.
Ага, хорошо.
Вот. Ну, у меня есть iPad, я могу писать на iPad, либо с лэптопа их вот листать и писать на доске, просто как бы уточнить, как.
Да, хорошо, отлично.
Хорошо, ладно, тогда до скорой встречи.
До свидания, спасибо.